Carbonyl compounds undergo nucleophilic addition rather than substitution at oxygen because the carbonyl carbon is electron-poor and more accessible to nucleophiles, so nucleophiles attack carbon and the oxygen stays bonded, often forming an alkoxide that is then protonated to give an alcohol. Acyl substitution can occur only when a good leaving group is attached to carbon, such as in acyl derivatives. Think of a carbonyl like a small house where the carbon is the front door and the oxygen is a strong porch railing. The oxygen pulls electrons toward itself and makes the carbon door look empty and inviting to guests with extra electrons, called nucleophiles, so they go straight for the door instead of trying to yank the railing off. When a nucleophile arrives, it pairs up with the carbon and the oxygen ends up holding extra electrons, like someone leaning on the railing, which then gets a proton later and becomes neutral. So the overall result is addition to the carbon and retention of oxygen. Only when the carbon has a group that can leave easily, like in carboxylic acid derivatives, will the process look like substitution at the carbonyl carbon rather than simple addition. The shape and electron distribution of the carbonyl make direct attack at oxygen both energetically and sterically unfavorable under normal conditions. Many students think oxygen itself gets replaced because oxygen is reactive, but oxygen usually only changes its bonding temporarily and stays attached. The tip is to track electrons with arrows and check who becomes negatively charged after the attack to see that oxygen remains. Another common mistake is ignoring the role of leaving groups. Remember that substitution at the carbonyl carbon requires a good leaving group attached to carbon. Otherwise, addition is favored. Some learners forget to consider protonation steps that stabilize intermediates, so always include proton transfers when writing mechanisms to see the full path to products. For more videos and clear explanations about carbonyl reactions and mechanisms, visit www.gumballdegree.com.